I wanted, although the time is short, to just briefly go back to the very beginning of what I was talking about, because it seemed from some of the questions I got both during that section and also in the ensuing 24 hours or whatever it's been, that a lot of people didn't get where I was going with the whole tier notion here. So to be clear, tier 1, the point is there are some reasons why you are almost absolutely going to have to supplement. And the first issue is basic, adequate nutrition, don't die of scurvy sorts of issues. And that means, first off, identifying how much you need. And what I'm trying to indicate here is that with the exception of vitamin D, I think the DRIs, the current versions of the RDAs, are good science and you should look at them. But because of the possible issue that CR may create induced deficiencies in these nutrients, it makes sense to go with multiples of the RDA. Now, by this I don't mean the old megadose notion of, 10, 20, 30, 100 times the RDA, but, 1.5, 2 times the RDA. I can't give you a number to target. I mean, this is just too fuzzy a notion that, we have at least some of these nutrients might be missed in, but I'm hoping that if you go with even multiples, that you will at least not have active deficiencies induced by things like bad zinc to copper ratios, this kind of thing. And then if you've got a specific disease, and we have some specific diseases for which specific supplements are effective, like hyperlipidemia and niacin, folic acid, it looks like probably for a family history of colon cancer, strontium, vitamin K2 for osteoporosis, then, that's a specific disease for which there is extremely strong evidence that you can avoid that disease. So these are cases where I think it's almost a no-brainer. You should be taking a supplement. The second phase stuff where I got into trying to avoid disease risk, I guess my point was there that we don't have evidence that supplements, as opposed to, foods on which supplements can be modeled, impact there very much, and our diets are already very good anyway. And that if you're going to do that, there's a much higher level of uncertainty in terms of whether it's going to be effective and what the effective strategy is. So the idea there simply is that the more you can mimic a good diet in various ways, the more likely it is you're going to get some kind of benefit out of that supplementation program, it would seem. So basically look at what good diets are composed of, and the key problems that I've seen are that the wrong molecules have been used, the wrong dosages have been used, and that a lot of molecules present in healthy diets for which there is good reason to believe there is a health benefit to have not been included in supplements, or molecules for which there is no reason to believe are going to be of benefit have been thrown into supplements as well. So I hope that sort of makes clearer the strategy and the point behind those two supplements and how you can empirically apply it. Does that help anyone at all? Yeah.
Yes.
Okay. Good. But what we really want to do, because I mean, the fact is, avoiding disease risk when you're already a healthy person is not going to gain you a lot of time. The evidence appears to be that if we could completely wipe out cancer from human existence, we would gain less than or equal to 3 years of life. If we could utterly eradicate heart attacks, it's about the same number. You wipe out the big killers, all circulatory disorders, cancer and heart disease and diabetes, you're looking at 15.3 years, and I'm much greedier than that. CR, I mean, I think Sherm's numbers, when I crunch them over again in my head, are probably about right. I mean, it's sort of depressing. So certainly there is the urge to slow intrinsic aging per se, and you want to do that with supplements, and here again we get into much hazier territory because there isn't even yet the suggestion in terms of hard data that anything is going to slow aging per se. So if we're going to try and do that, and again this is raw speculation at this point in a lot of ways, what kind of strategy are we going to use? The strategy that I'm proposing is what factors are associated with maximum lifespan across mammalian species which are also moved in the same direction by caloric restriction in the rodents. And to the best of my knowledge, there's only two reliable examples of that, one of which is issues related to free radicals in the mitochondria. Specifically, the rate of production of mitochondrial free radicals per unit of oxygen consumed, the amount of damage to mitochondrial DNA, and importantly, the rate of damage to nuclear DNA is not correlated with maximum lifespan. But the rate of damage to mitochondrial DNA is. The susceptibility of mitochondrial membranes to oxidative damage, all these factors clearly tied in with mitochondrial free radical and damage to the mitochondria are both correlated positively or inversely, depending on which one you're looking at, with maximum lifespan across species, and are moved in the same direction by caloric restriction. This, incidentally, although I don't want to get too far into this controversial pet theory, is why I suggest that people should avoid long-chain fatty acids, in particular docosahexaenoic acid, DHA. We know that across species, when I talk about the mitochondrial peroxidizability index, that mostly is composed of the amount of DHA in those membranes. And when you compare species, you see pretty consistently there's a much lower level of DHA in their mitochondrial membranes in more longevous species. CR does reduce that index and reduce the amount of DHA in their membranes, and in fact, when you take rodents at least and feed them DHA, the amount of DHA in their mitochondrial membranes goes up. So that's all a strong series of correlations suggesting that DHA is not a good idea. So to skip over a few sort of issues, you want to actually reduce the production of free radicals at the mitochondrial level. How are you going to do that? I expect most of us are at least loosely familiar with this, but I want to get into it to explain some of the details here. We all know the mitochondria, well, I think we all know the mitochondria are the major source of free radicals to which we're exposed. The way that happens is when you take the energy in food, basically you strip that down and its electrons transported as negative hydrogen ions. Those are taken up by NAD, which is an enzymatic cofactor. You take that up and you form NADH. NADH takes those electrons basically and puts them through these complexes of the mitochondria, and as it does that's used to basically create a pump that then drives what is literally a turbine, which ultimately generates energy. The problem is, as those electrons are handed as NADH gives those electrons to complex 1, it hands them over from complex 1 to complex 3 via coenzyme Q10. And as coenzyme Q10 accepts those electrons, it becomes a certain species of free radical, the eubisemiquinone radical. And it's fairly reactive, and it can hand those electrons off to molecular oxygen and form superoxide. So the key point here is that the mitochondria produce free radicals because of the taking of electrons into complex 1, handing it to coenzyme Q10, and coenzyme Q10 can, under certain circumstances, fumble them. Now, I'm getting into that detail for the following reason. Work by Barja now seems to demonstrate that the reason that we've known for about 10 years now, and it's been validated repeatedly, that CR rodents actually do produce fewer free radicals, despite the fact that, by almost universal agreement at this point, metabolic rate, oxygen consumption is not lowered. So somehow they're, on a per cell basis, just as much electrons are fluxing through that cell, but they're not producing those free radicals. So what's going on? Well, Barja appears to have demonstrated that what is going on is that for whatever reason, complex 1 is not accepting as many electrons. So NADH is not handing as many electrons to complex 1. So one approach to do this would be to find some way of reducing the amount of electrons that are being fed into complex 1 from NADH. What is happening in CR, according to de Grey, you guys have got copies of these diagrams, so if you want to refer back to them, or even, rather than looking at these images, which may not be coming through very clearly, what de Grey believes is going on is that when those electrons, which would normally go through the citric acid cycle and be passed on into complex 1 or under other circumstances to complex 2 and produce these free radicals, the calorically restricted organisms are instead putting out, and I have a picture on this, but I'll just skip ahead. There's an alternate way you can get rid of NADH, and that is there is a thing on the cell surface, the plasma membrane redox system, which is normally used for other purposes, which he hypothesizes you can reverse transport those extra electrons out. Under those circumstances, oxygen would accept them and form water the same way you would at the tail end of normal oxygen consumption in the mitochondria. I'm going far too fast, I apologize.
Too low on the screen for people to see it.
Oh, okay. The point is there's an alternate way you can get rid of those electrons once they have been fed to NADH that still consumes oxygen and therefore accounts for all those sort of paradoxes, which is you spit those electrons through NADH out through this cell surface protein called the plasma membrane redox system, PMRS. The reason why I wanted to go into that level of detail on those issues is that there's the apparent reporting by Hagen and Ames that R plus lipoic acid, and it is the R plus form of lipoic acid, is actually reducing the production of free radicals by the mitochondria in their rodents. Now, that was greeted with a fair amount of skepticism at the time, and it was felt by a lot of people, including Aubrey de Grey, and also in a private conversation I had with him, with Torrey Hagen himself. Despite the fact that he reported lower production of free radicals, they can't, the methods they're using don't actually allow them to directly assess that it is actually the production. So theoretically, lipoic acid might be acting as an antioxidant and just sucking up those free radicals as they're being produced so close to the mitochondrion that they don't detect the fact that they're being produced in the first place. However, there's a hypothesis that came